Do you like taking about 100 dot products? If so, this video is for you. We're going to be going over how the Gram-Schmidt process works and hopefully not going insane in the process. So the first step of the Gram-Schmidt process is always labeling these. We're going to call this U1, U2, and U3. I'll just lay out the general formula that we're using for finding all three of these basis vectors, and then we will go apply them in all the other questions without rewriting all these formulas. So V1, our first basis vector, is 1 over the magnitude of U1 multiplied by U1. So we just normalize U1, and that's that. We're done. And that we're calling V1. Now we can take V2 as the normalized. So I'll just know that we're taking the unit. We're finding the unit vector of what we get in the end, because this is a little weird to write. We're gonna take U2 and subtract from it U2's projection onto V1. That will give us V1 dot U2 over V1 dot V1 multiplied by the vector V1, and then, as I said, all of this is going to be divided by its own. You know what I'm saying. We'll normalize it. Then for V3, that's just going to be U3 minus the projection of U3 onto V1 minus the projection of U3 onto V2. So that gives us U3 dot V1 over V1 dot V1 multiplied by the vector V1, and then we're subtracting U3 dot V2 over V2 dot V2 multiplied by the vector V2, and then we'll normalize this one and we'll be good to go. So let's apply this. V1 is just 1 over the magnitude of U1, which is 9, 13, 14, so root 14 multiplied by 3, 1, negative 2. V2 is U2, 2, negative 1, minus the projection of U2 onto V1. So that will be V1 dot U2, so 1 over root 14 multiplied by 3, 1, negative 2. We're dotting that with U2, 2, negative 1, over 1 over root 14 multiplied by 3, 1, negative 2, dotted with 3, 1, negative 2 multiplied by 1 over root 14, and then we're multiplying this entire thing by the vector 3, 1, negative 2 multiplied by 1 over root 14. So you should notice something. We have two 1 over root 14s on the top and 2 on the bottom. So with all of these computations, it'll simplify your life a lot if you ignore whatever is outside of our vector here, and we just deal with the vector components themselves, not any constant multiple outside. So let's just compute this. We will get 6, 5, 7 up here, and 9, 10, 14 down here. And usually you do get some nice numbers, like things will simplify down to 1/2 or 1/3, and everything's great. Although there was one question where you got 22nds and 11ths, and that ended up leading to the correct answer, but it's a little sketchy to get those numbers sometimes and not really know what to do. So we can divide this out, get 1/2 times that vector, and instead of having to deal with fractions, we know that since we're normalizing this in the end, all we can do to solve this problem is multiply both these vectors by 2, so 4, negative 2, negative 2, and we can just get rid of that negative 1/2 as long as these two have the same multiple of each other, if you know what I mean. The normalized vector that we get in the end will always be the same. So this subtraction will give us 1, negative 3, 1, negative 3, 0, and we'll have to multiply by 1 over root 10 to get v2. So now we have v1 and v2, and we know our answer there. The nice questions for Gram-Schmidt work like this, where if it's clear that you know what you're doing, there's only one answer choice, halfway through when we found v2 that solves the question. So we're not like stuck between this one and another one, and we have to go find v3 to make sure. And there are enough of these problems, and they're time-consuming enough that in the future, later on this video, I'll probably just stop there, because really you only need to see this kind of thing once to get what's going on. But for the purposes of this first question, we're finding v3. That will be u3, 1, 1, 2. Subtract. We're going to subtract from that the projection of u3 onto v1. That will be the dot product of u3 and v1. So 3, 4 minus 4 is 0. Okay, so that entire component will go to 0. And then we're subtracting the projection of u3 onto v2. Got to be careful with my wording there. We will get 1 minus 3, so negative 2 divided by 10 multiplied by 1, negative 3, 0. This will become plus 1 over 5, so let's multiply both these vectors by 5. We get 5, 5, 10, and this gives us 6, 2, 10, which we can simplify down to 3, 1, 5. The magnitude of that is 9, 25, 35. So square root of 35, and there we go. There's our third basis factor, and it agrees with the answer choice we already chose. 17, here is S, the set of these vectors, and it is a basis for R3. Let's apply the Gram-Schmidt process to obtain an orthonormal basis. So yet again, V1, and sorry, I forgot my first step. This is U1, U2, U3. But our first basis vector, V1, is just the normalized version of U1. So that's 1 over root 5 multiplied by negative 2, 0, 1. And looking at our answer choices, that gets rid of one of them, but not any of the others. So there's our first basis vector. Now V2 will be U2, 2, negative 1, negative 1, minus the projection of U2 onto V1. So we're taking the dot product of U2 and V1. That gives us negative 4, so minus 1 is negative 5. And we're dividing by V1 dot V1, which is 5. And then multiplying that by V1. So negative 2, 0, 1 right there. This simplifies down to plus. And we get what? 0, negative 1, 0, negative 1, 0. Okay, that takes it down to just C and D. And since this is already of length 1, we don't have to do anything to it to normalize it any further. Let's find V3. That will be U3, which is 4, negative 4, 3. And we'll subtract from that the projection of U3 onto V1. So that will give us our dot product on top will give us negative 8 plus 3, so negative 5. And we know that the dot product of this with itself gives us 5. We're multiplying that by V1, so 2, negative 2, 0, 1. And then we're subtracting from that the dot product of V2 and U3, which is 4, over the dot product of V2 with V2, which is 1, multiplied by V2, 0, negative 1, 0. So overall, we are adding 4 there. This is plus, and we can put this 4 in here and compute. We get 2, 0, 4. We can simplify that down to 1, 0, 2, multiply it by 1 over root 5, and there is our V3. So that leads us to answer choice C. 20, let's perform the Gram-Schmidt process. Who would have guessed? So normalizing our first basis vector, well, yeah, the first vector in the setup here to get v1, but labeling these u1, u2, u3, I keep forgetting to do that, we get 1 over root 6 times 1 to 1. Yep, okay. So now v2 will be u2 to 1, negative 1, minus the projection of v1, of u1 onto v1. So the dot product of this bit of v1 and u1 gives us 4, 5, 6. Oh wait, that's u1. No wonder it's the same. Okay, u2 is what we're taking the dot product of with v1. That gives us 2 plus 2, so 4 minus 1 is 3, over the dot product of v1 with v1, which is 6, multiplied by v1, 1, 2, 1. This is negative 1/2. We can multiply both vectors by 2 and compute. We get 3, 0, negative 3, or otherwise known as 1, 0, negative 1 times 1 over root 2 to simplify and normalize everything out. So now v3, blah, 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 is going to be u3, 3, 2, 2, minus the projection of u3 onto v1. That gives us 7, 8, 9, divided by v1 dot v1, which is 6, multiplying that by v1, 1, 2, 1, and then we're subtracting out the projection of u3 onto v2, which gives us 1 on top, and on the bottom we get 2, and then we're multiplying that by 1, 0, negative 1, and if we simplify this all out, we should have our answer. Okay, this can become 3 over 2. Let's multiply all of our vectors by 2. We get 6, 4, 4 here. That gets rid of those denominators. We can make this 3, 6, 3, and that guy just stays the same. So computing our answer, we get 6 minus 3 minus 1 is 2, 4 minus 6 minus 0 is negative 2, 4 minus 3 is 1, plus 1 is 2. We can make this 1, negative 1, 1, times 1 over root 3. And there is our answer. These are the scariest. They've only done this to us once, but there's something not fun at all about not being able to tell if you're on the right track like we can in these questions, because here they just throw you in the deep end, and you got to make it through the whole process correctly and find u3 on your own. So that's not fun. Also, I hope I didn't trigger anybody by calling these guys u1, u2, u3 when they were asking us for those. Too bad if I did. Okay, 22, let's consider the basis for R3 given here. Let's apply the Gram-Schmidt process. So v1 is just the normalized version of u1, u2, u3. So the normalized version of u1, that's 1 over root 5 times 2, 1, 0. So we can get rid of A, and we can get rid of E. Great. Now v2 will be, and I like to circle those. There we go. v2 will be u2, 0, 1, 2, minus the projection of u2 onto v1. That's the dot product of u2 and the vector part of v1. That gives us 1 divided by v1 dot v1, which is 5, multiplied by v1, 2, 1, 0. Let's multiply both these by 5. We get minus there, and 0, 5, 10. That gives us negative 2, 4, 10, which we can simplify down to negative 1, 2, 5, and multiply by 1 over 25, 26, 27, 28, 29, 30. 1 over root 30, and there is our v2. Just as I was saying before, this is one of the nice questions where you can only do 2 steps and end up with the answer, but I'm in a good mood right now. So, and yeah, we only have 1 question left, so might as well go through the whole thing. V3 will be U3, which is 2, 1, 0, minus the projection of U3 onto V1. So that dot product on top will give us 4. We're dividing by 5, multiplying by 2, 1, 0. And then we're subtracting out the projection of U3 onto V2. That gives us -2 plus 2 is 0. Okay, so we get 0 over something multiplied by something. Doesn't really matter. Let's multiply both these vectors by 5. We get 10, 5, 0. Multiply this guy by 4, or put that 4 in here. We get 8, 4, 0. And then we compute 2, 1, 0 times 1 over root 5. And, oh wait, am I doing my math? Am I doing my math correctly? I don't think I am. Let's go back and see if we can figure out where that mistake happened, because we should be getting this 1 over root 6 thing right here. Where did I go wrong? Oh, I know where I went wrong. So, no, I don't. No, I have no idea where I went wrong. Let's just restart this whole step. And if you're comfortable with this, feel free to skip ahead. So we have 2, 1, 0, and we are subtracting out the projection of U3, which is 2, 1, 0, onto V1. That gives us. Oh, that's what I did. I wrote, instead of 2, 0, 1, I wrote 2, 1, 0. Let's see, 2, 0, 1. So that should give us the answer then. 2, 1, 0, 2, 0, 1 dotted with 2, 1, 0 gives us 4. There's our 4 over 5 times 2, 1, 0. And then the dot product of 2, 0, 1 with -1, 2, 5 is -2 plus 5. So we're subtracting 3 over 30. Look at that. That's 1 over 10. Let's make this 8 over 10. We're multiplying this by -1, 2, 5. Okay, let's multiply all of our vectors by 10. We get 20 here, 10 here, 16, 8, 0 here, and that there. Okay, so subtracting, we should get something that simplifies down to this answer. So 20 minus 16 is 4, plus 1 is 5. -8 minus 2 is -10. Okay, yeah, we're looking good, because this gives us 5. This can be reduced down to 1, -2, 1 times 1 over root 6. There we go. There's our third basis vector. Finally, ooh, look at that. I didn't mean to order it this way, but we have a 4-dimensional example last. But this one's actually super easy because we have only ones to deal with, so our dot products are pretty trivial. So V1 is just the normalized version of U1, which is 1, 1, 1, 1 times 1 over root 4. 1 over root 4 is just 1 over 2. So let's do that. And we see that that lets us take out answer choice C. V2 is equal to U2, 0, 1, 1, 1. Look at that. Now they're using my naming scheme with U1, U2, U3, but then right up here they're asking us to find U1, U2, U3. That's kind of, don't like that. This is completely unrelated. I'm sorry. And I don't know. I'm sorry about this. But sometimes when they want to write the subspace of 3x3 matrices, they say M33, and other times they say M3x3, and that bugs me. That's all. Okay. We're taking U2, which is 0, 1, 1, 1, and subtracting its projection onto V1. So that is 3 over 4 multiplied by 1, 1, 1, 1. Multiplying everything by 4, we get 0, 4, 4, 4 minus 3, 3, 3, 3. This gives us -3, 1, 1, 1. And we can normalize this by multiplying it by 1 over 9, 10, 11, 12, right? Yep, okay. And now that leads us, well, actually, not much of anywhere. We're still stuck between three answer choices, but at least we know we're on the right track. It seems like we've made the correct choices up until this point. So V3 will be U3, which is what? 0, 0, 1, 1. We're subtracting its projection onto V1, which I'll circle, and this guy needs a circle too. Those aren't really circles, you know what I mean. We're okay. Okay. U3 dot V1 gives us 2, and we're dividing out U1 dot U1, which is 4, multiplying that by U1, so 1, 1, 1, 1, and then kept saying U1. You know what I mean to say in all of these. I meant V1. Naming things U and V is a bad idea for me. Okay, now finally we're subtracting out the projection of U3 onto V2. That gives us 2 over 12, so 1 over 6 multiplied by -3, 1, 1, 1. Okay, this is 1/2 or 3/6. Let's multiply everything by 6. We get 6, 6, 3, 3, 3, 3, and nothing changes right there. Finding our final answer, what do we get? -3 plus 3, so 0 should be our first entry. -3 minus 1 is -4. -4, -4. So we can simplify this down to what? I can't read. There are 6's here. There we go. So I gotta recompute that. -4, and then 6 minus 4 is 2, and then we'll get 2. So this can be 0, -2, 1, 1 over root 6. Where is that? That is right there. Awesome. Great. We're done. That's it. This is not a fun topic, but it's one that if you know how to do it, you will get the question right. They can't do much to trick you. You just got to put the work in. Yeah, it's not too bad.